Hello, students. Today we want to continue with our study of the theory of derivatives. And like I said before, we work through the definition of derivative. We work through basic formulas for derivatives. And then last lecture, we looked at some more sophisticated results having to do with products and quotients. And we learned that there are derivative formulas for those types of functions. And they turned out to be very, very useful. And if you're thinking, you saw in a previous set of lecture notes, a proof for the product rule with positive integer powers. Now, you might have thought that for the negative integer powers, you can actually employ the quotient rule and get that result. And I would like to add that eventually. Maybe I will say something about that towards the end of this lecture, just to kind of apprise you of the fact that we continue to investigate the power rule, even though we were going to be happy to use it whenever we need it as we move through the theory in the course. Now, the main result today is called the chain rule. So I mentioned this several times before. When we have compositions of functions, which occur very often in mathematics and STEM, we really need a method to differentiate them. That is, if we have the composition of two functions that have derivatives, is it true that we can actually write a formula? And basically, yes. And the nice thing about it, it has a formula that's easy to remember, similar to that of the product rule and the quotient rule. So you might be thinking, with every problem that we do, as we apply the derivative, we always have the indeterminacy of the definition, the 0 over 0. And we have to work beyond that. We have to figure out a way to get past that indeterminacy. And when we can do that, we can produce a very, very useful formula. So we have to acknowledge the fact that our definitions are abstract and unrelenting when it comes to algebraic manipulations in order to uncover characteristics that are important. That is, if we have certain hypotheses, then we apply those hypotheses and we move to a result that we can use. So let me share with you just some fundamental theory that will allow us to write the chain rule. And you will find the chain rule probably to be one of the most important results that you use for the next few lectures. And as we get into more theory, we will talk about other results that will again have far-reaching consequences for us. So let's share the screen. Now, as I said before, we just need a way to overcome the indeterminacy of the definition. And this is very simple here. It only deals with the definition of the derivative. And if you look at your lecture notes, you see something similar. I just wanted to rewrite this and share with you some of the basic concepts you already know, and then show you a slide on the chain rule that gives us the formula that we need. Now, when we look at the definition of derivative, that is g prime of c, and we've written this so many times, you probably know it by heart. The limit is x approaches c of g of x minus g of c divided by x minus c. Now, what we're interested in, at least for the chain rule, is this difference here, g of x minus g of c. And so we want to do some estimates to see if we can actually determine a function that will allow us to write this difference in a cogent way that will not only allow us to remove the indeterminacy, but to also include the derivative. So what I've written here, for x reasonably close to c, we can now think of removing the limiting process and cross multiplying. And when we do that, we have g of x minus g of c minus g prime of c times x minus c. And so what we want to think of that is the error. That is, as we get closer and closer to c in the limit, we produce the derivative. So if we're reasonably close to c, how can we come up with some term that will make up that difference? Well, we can do it this way. So once we look at this, when we think about the error here, now we can simply factor the x minus c from both terms. So of course, that will leave us with the g prime of c, and then of course, we have to divide g of x minus g of c by x minus c. But that's very convenient because that's the difference quotient for the derivative. And so what we can do is define s of x to be this function here. Now, as I just said, we know that s of x has some really good properties. That is, now if we take the limit as x approaches c, we see that the first expression approaches g prime of c, and we're basically taking an expression here that has no impact on c in the sense that there are no impact on x, even though x is approaching c, there's no x dependence. So this is constant. So this is approaching g prime of c. So the difference between this particular expression and g prime of c in the limit would indeed be 0. So we see that the limit of s of x as x approaches c is indeed 0, what we've defined here. So now we can go back to this expression and say, okay, well, let's just transpose everything. So this is s of x times x minus c. And so we'll just transpose this term and have g of x minus g of c is now equal to g prime of c times x minus c plus this new function times x minus c that we have already defined. And that gives us an expression for the difference that is of great convenience to us. So now I just put it in a box and I called it a key construction because all we've done is use the definition of derivative and manipulated the definition of the limit in a way to come up with this function s of x. And so now we see the difference, g of x minus g of c, as we've noted here, is just g prime of c plus s of x, factoring the x minus c in a more convenient form. And we observe the fact that the limit of s of x as x approaches c is 0. So this gives us a way to write the actual difference here from the definition of derivative as a product of two very convenient functions, and this being very useful because this is what we're always looking to absorb. Okay, so now this sets up for the chain rule. And what I wanted to say here is when we start thinking of compositions, if we're just going to look at f of g of x, so the composition, at least the statement in the theorem, would be f composed with g of x. But then, of course, the definition is just substituting g of x into f of x. So in order to do that and use this construction a second time, we can now define u to be g of x just for convenient notation and u sub 0 to be g of c. Now, we can now think of saying f of g of x minus f of g of c using this and this particular construction of the composition. So we would have, comparing it to this, f prime of u sub 0, and then another function that we're just going to call nu or v of u, just like we have here, times u minus u0. And then, of course, from this construction, we know that v of u approaches 0 as u approaches u sub 0. So we're using this construction on f. But now what you can see is if we now think about how we actually wrote the last construction here, let's go in and replace everything. So for u, we write g of x. For u sub 0, we write g of c as we've defined here. And then let's just go ahead and write these with the compositions, replacing, of course, u sub 0 with g of c and u with g of x, just like we did here. Now you can see this just kind of keeps cascading. We can now think of g of x minus g of c defined as we've done here. And that would just give us g prime of c plus s of x times x minus c. And notice what I did here. I put a red box around this. Factor absorbs x minus c in denominator to relieve indeterminacy. So when we actually divide the difference of the function compositions, that is the composition evaluated at x minus the composition evaluated at c, we divide by x minus c. And of course, that x minus c is absorbed, by this one. And that is what happens. That is what relieves the indeterminacy. So that's the key construction here that I've written that allows us to move this forward. Very simple, but very much needed, because when you think about the definition of derivative, it's what it needs to be, but it's not always so user-friendly. Now that we know how we go about setting up the construction here, we can now state the chain rule, which I have here. And what I've written here is from your lecture notes, and it's just the same thing that I was just talking about, where you just basically replace the function with all of these terms that we've just talked about with the v of x and the s of x. So that's all repetitious, but notice here, I've just stated everything just like I did on the previous page. So how does the chain rule go? And why does this construction make the chain rule simple? Well, we're going to suppose that the inner function, again, we're going to think of an inner function. If it's f composed with g, that would be g, but whatever letters you like to use, that's your choice. So the inner function g is continuous on an open set I containing c. You can think of I as just an open interval. And f is defined on the range of g. Well, we tacitly assume that the function is composition is well defined. Otherwise, it would be void. There would be nothing to work with. Now, what we do here, and this is how we get the differentiation in at c, we assume that f prime exists at g of c. Okay, we can actually differentiate f and it exists at g of c, and g prime exists at c. So that kind of makes sense, because if we look back here, we see we need a derivative at g of c, and we need a derivative here at c. So that's setting up for that. So our statement of our theorem uses what we just set up. And then the composition f composed with g is differentiable at c. And here's the beautiful part of the theorem. And I would say this is probably easier to remember, even though I said the product rule and quotient rule are easy to remember. When we take the derivative of the composition, that is f composed with g prime, the derivative at c, we just have the derivative of the outer function defined at g of c, or evaluated at g of c, times the derivative of the inner function. So that's the key part. Students initially always remember the outer function, but then sometimes forget to tack on the factor of the derivative of the inner function. So that is the piece that we were needing. If we have the square root of x squared plus 1, the inner function is x squared plus 1, its derivative is 2x. So we've got to have a factor of 2x in the derivative. And then, of course, we'd have to be able to apply the power rule to the square root, x squared plus 1 to the 1/2. So we basically use the chain rule to generalize the power rule. So we've got this great power rule that says we can bring the power down as a coefficient and subtract 1. That's what we've been doing. And now the chain rule will say, add the additional factor of the derivative of the inner function. So again, think of this as the derivative of the outer function times the derivative of the inner function. And of course, if you just want to write this as a formula, just replace the c's with x's as we've been doing. So you can say this. In this case, this is outer derivative. Speaking of outer function, and this is the inner derivative. And the way these are connected is through the product. You have the product of the outer derivative and the inner derivative. And now, just like we had before, the setup is exactly the same as on the previous page. We rewrite the difference of f of u minus f of u sub 0. And also, we rewrite the difference of g of x minus g of c, just like we did on the previous page. So all of that is repetition. And so the only difference now is that we just go ahead and take the limit as x approaches c, and we divide all of that by x minus c. So at this point, what we see, if we just move to this part of the proof, we know this is where we were before, and now the x minus c's absorb. And that's what creates this simple limiting process. And so now we have the limit of a product, which is the product of limits. We know that as x approaches c, the g of x by continuity is approaching g of c, or u sub 0. So the b term is becoming very close to 0. The s of x, again, as x approaches c, is becoming very close to 0. So both of these terms zero out just by our hypotheses right here and here. That's, again, the key construction. And of course, these two terms have no x dependence. So we just end up with f prime evaluated at g of c times g prime evaluated at c, which is exactly this, the result of the theorem, by the continuity of g. The continuity of g is essential. That's why we have this in the hypothesis. So again, if you want to think of this as a formula, let me just kind of squeeze in the of x here. I kind of left that out, but I think it's clear that it should be there. So if you want to think of this as just a formula, replace the c's with x's. So we'll just say the derivative of f composed with g evaluated at x is just the outer derivative at g of x, times the inner derivative at x. So again, we often like to just work on a formula, look at the formula and see what it gives us. That is, when we first started, we were trying to find the domain of differentiability. And then I said, again, we can look at that, but we can also think of the function that we've differentiated as we move to the derivative as just a brand new function and treat that as we would any function. So we often like to write our formulas with x just because it gives us that computational push as we're looking at derivatives, the first derivatives or whatever, or we take a second derivative of the first derivative. So remember what makes the derivative so powerful is that we were able to evaluate it. We're able to find horizontal tangents. That is, if indeed the derivative can be 0. We're going to learn a lot more about the theory of differentiation as we move forward. But what's important is that we can think of this derivative as a new function. It has certain qualities, and the qualities it has tells us about the original function. Like I said before, horizontal tangents. And then, of course, if we have values of x in the domain for which the derivative becomes infinite, that means we have infinite tangents, that is, vertical tangents. So we look at the derivative as being a spotlight on the original function. It is a function itself, but it carries information about the original function that is very important to us. So we keep thinking, if we know more about the derivative, the first derivative, we know more about the function as a curve, as a graph of the characteristics that it should have. So as we continue to analyze the first derivative and eventually the second derivative, we will be able to sketch a function with complete knowledge. Again, we only understand how a function looks graphically or as a curve by a complete understanding of the function. We don't get the graph first, we understand the function, and then we can sketch it as a curve. So let's look at some examples. I think you'll find that in general, working with the chain rule is very much like the process of working with the product rule, working with the quotient rule, working with the power rule. We just simply want to add the idea of composition to the mix. Now, just to reiterate, let me write this down, the generalized power rule. And most students like this because it gives you a nice statement of the power rule, but thinking more in terms of a composition. So before or earlier, and we can use any variable, we're just thinking of a non-composition. If n is is natural number or integer or even rational, we've extended it to the rationals, even though we haven't offered the best proof of that. That's going to come with a technique called implicit differentiation, and I'll share that with you then. So for instance, for right now, we're stretching a little bit. We're assuming that we have validity for n, a rational number, and the result looks like this. So if we have x raised to the n prime, just looking at it like a formula, then this is n times x raised to the n minus 1 power. That's the power rule. Now, the generalized means that we are now looking at replacing x with a function of x that maybe is more complicated. Okay, so we're thinking, you know, if we have the chain rule, I mean, of course, it could be that simple. I mean, but the chain rule basically is saying that now we have an inner function that's different from x. So for instance, let u of x be a real expression. So we are now allowing the inner function in this case to be more grand, so to speak, more complicated than just the x variable. Then, and again, we'll take n as a rational number. Then the derivative, just looking at this like a formula, will now be the power rule, the derivative of the outer function, which is u to the n. We get n, u to the n. And then I'll just put a little dot here for times the derivative of the inner function. And we'll just say u prime. So here is the, oh, of course, better subtract the 1. Here is the outer derivative of the outer function. I just say outer derivative, a little bit shorter. And here is the inner derivative. So this is very, very powerful. And the reason we're stating this is, again, this is just a direct application of the chain rule. That is, now we assume that u is an inner function. And of course, if it were just plain old x, u prime would just be 1. So it's still consistent, it just kind of overkill. So when the complication arises that the inner function is other than just x, we can apply the chain rule. So again, remember, we have the outer derivative, which is the derivative of the outer function, times the derivative of the inner function. And of course, the outer derivative requires the power rule, And then, of course, the chain rule requires that we multiply by the derivative of the inner function. So here's a simple example. We'll do some examples that kind of take all the different theorems together. But say you had something very straightforward like this. Say you have h of x equals just the square root of x squared plus 1. This is a very nice function. Its domain is all reals. The domain of h is all real numbers. Now, we can think of this as a composition. That is, we could just write it as x squared plus 1 to the 1/2 power. And so now we have an outer function, which is the square root function. So we're thinking of the n as being 1/2, and the inner function, or the u, being x squared plus 1. So then h prime of x will just be the derivative of the outer function by the power rule, subtracting 1, always remembering to subtract 1, and then multiply, and put a little dot there just to remind yourself that juxtaposition means multiplication, but it's good just to have there as a mental boost. We take the derivative of x squared plus 1, which is just 2x. And now, of course, the 2's will absorb. So now you see how powerful this is, and how we were really struggling before. I mean, now we can differentiate cosine of 2x because we know the inner function is 2x and its derivative is 2. Before, we couldn't do it unless we wanted to use a trig identity. So even though compositions can have a very simple look to them, we were still struggling as to, well, how are we going to differentiate this? It's not an x. The inner function's not an x, so what do we do with it? So now the 2's absorb, and we just have, if you want to take the square root downstairs, we just now have x divided by the square root of x squared plus 1. So this indeed is different and is essential. The chain rule is an essential tool. And of course, you can have more than 2 functions being composed. That's why it's called the chain rule. Because if you have 3 functions, then you're moving to a product of 3 derivatives, because now you have a function of a function of a function. And that just means lengths of the chain rule. So very, very, very powerful result. It is an essential result. And when you do the STEM, mathematics, the science, the engineering, a cornerstone of the theory of calculus. So let's look at some examples. Again, the generalized power rule simply gives us a means of extending the power rule that we learned earlier in our pursuit of understanding the derivative. So now let's look at an example. And we want to apply the differentiation process. So we have y equals x squared times 49 minus x squared to the 1/2 power. Now, in some cases, we want to find horizontal tangent, so we just want to take a derivative and clean it up and figure out where it could possibly be 0 or undefined. That'll be a common occurrence in a lot of the problems that we do. So we need to get good at cleaning up the computation of the derivative so we can analyze it just like we are in a college algebra class. So what we want to do here is compute y prime. So lots of times problems that we have are very straightforward. The algebra is minimal and we're just applying definitions. Now, when we do derivatives, we've got a lot more work to do. It's not that the work is overly difficult, but we have to be a little bit more vigilant about our process in making sure that we follow the theorems exactly. So notice here, this is a product So this is where we combine the product rule. We combine the product rule with the chain rule. You'll enjoy using this theorem. It is a very powerful result. So now y prime, again, we'll start with this being the first function. We'll take the derivative of that and get 2x and multiply by the second function, just the product rule. So good for that one. Now we have the x squared, and now we multiply by the derivative of the second function, which will require the chain rule. So we have 1/2 the generalized power rule, 49 minus x squared to the negative 1/2. Again, applying the power rule to the outer function. And then, of course, the derivative of the inner function would just be negative 2x. So you can say minus 2x. So again, if you recall, we will have many uses for the generalized power rule. Many uses. Now, what we want to do is clean this up a little bit so we can make it a little bit more user-friendly. Now, notice the 2's absorb, and we can combine some terms. So we have 2x, excuse me, 49 minus x squared to the 1/2. And then notice here we have an x and an x squared and a negative. So we have negative x cubed, 49 minus x squared to the negative 1/2. Now, just like you learned in pre-calculus, we can often, instead of maybe writing these as fractions and taking this downstairs, we can just factor the least power of the 49 minus x squared. That works really well when we've got the half powers here. And then notice, if you will, we can go ahead and factor, I don't know, we can go ahead and factor the x, and then we could probably factor the 2, but let's just see what's going to happen when we do this. So we'll factor the x, and then the 49 minus x squared to the negative 1/2. And now, of course, the x is gone. This factor must be manipulated to a 1 power to pay for the minus 1/2 here. And of course, the 2 is still there. So now when we compare this product and this, the product of these two factors, we get exactly that, which is what we should get. And then, of course, here, this has been extracted, but we still have the minus x squared. Now, a lot of times what we try to do is just get rid of all of the fractions. We can still factor once we clean things up a little bit more, but how you decide to do that is kind of a thing maybe involved more with personal taste and how you do your algebra. But there's certainly nothing wrong with doing things a little bit differently. The result will still be the same if we maintain good mathematics. So now we have what? X. I'll go ahead and leave this upstairs until we just move it downstairs. For now, we'll just leave it where it is. And then in here, we've got what? We've got a negative 2x squared minus a x squared. So that's a minus 3x squared. And then we have plus a 2 times a 49. So now we can think about some, more clever factoring. Now, notice, this is the derivative here. I mean, you say, well, where do I stop? Well, I want you to think of just working the derivative to a point to where you could actually analyze for zeros if they exist, or places where the function were undefined. Notice here the domain. You probably already thought about this. The domain of y will include what? -7 to 7, because we have 49 minus x squared. So any interval, any element in this interval will be fine with this square root. Basically, you can factor that and use absolute value. So the domain is very important here. So if you like, we can go ahead and factor a -3. So we're going to have a -3x, and I'm going to remove this downstairs, but that's going to give us x squared minus 2/3 times the 49. And then, of course, downstairs we have the radical. You can use the radical sign or just keep doing the 1/2. But notice now this is just a difference of 2 squares. So if you wanted to stop your derivative right here, you could, but I'm going to just keep moving it on to write this as a difference of 2 squares. So -3x and then x minus, of course, the derivative of, the square root of 49 is 7. So this will be a 7 times the square root of 2/3. And then we have x plus 7 times the square root of 2/3. And then we have the square root downstairs. So now what we're seeing, all of these are derivatives. Again, this would be a nice form to write. This would be a good form. It's fairly reduced. This is a form that we're looking at when we're trying to find horizontal tangents and maybe infinite slopes. So now we can see just by this, y prime equals 0 if and only if x is 0, or x equals 7 times the square root of 2/3, or x equals -7 times the square root of 2/3. So what we see here is that we have the existence of 3 horizontal tangents. And since -7 and 7 are in the domain, we also have infinite tangents. And we can say infinite tangents at 7 and -7. Now, of course, these are the zeros, and of course, this I can note as horizontal tangents. That's where they exist. We don't have that. Well, I'm not asking for the points here. You could compute those. But what's interesting about this problem is that because we're keeping track of the domain, we would think, again, if you notice this has got this nice symmetric domain. Y is even, it's an even function. And then, of course, the derivative is odd. We have proven that. And so we're thinking that we've got these nice horizontal slopes. So if you just wanted a cheap picture of this curve without even analyzing it anymore, it wouldn't be hard to do, even though this is very, I'll just say pedestrian. So like if we had like a -7 here and a 7 here, of course we've got a nice tangent there that's horizontal. So maybe we're moving up something like this and we're cresting at a horizontal tangent. And then we come down here smoothly. And then we're going to do the same thing on the other side because, of course, we're an even function. So that would just be just kind of a reasonable thinking of the function. That is, we're not at this point yet where we're talking about increasing and decreasing, but at least we know we would have a horizontal tangent here and here because these are just numbers. Again, this number is greater than -7, and this number is less than 7. So we're just kind of guesstimating where we would have these points. That is -7 root 2/3. and then 7 root 2/3. So we're thinking our theory is going to help us here. And yeah, the picture's not the best. So let's just see here. Like that. So again, we have a nice symmetry relative to the y-axis. So we're just thinking, at least from what we've learned about the derivative so far, we've got a horizontal tangent here, we have one here, we have one here, and here, of course, we have the vertical tangents. So we draw the graph so it mimics the vertical tangent, which we see from here. So just by knowing the derivative, we've improved upon what the graph is. We're not guessing at the graph. And so now what's left? What's left is that we have to have some kind of mechanism of showing that what appears that we've drawn here, even though we may not be exactly right, it appears that we have increasing, then decreasing, then increasing, then decreasing. Will the derivative tell us that? And then the function shape. I mean, we've got a concavity going on here that looks to be downward, but then it converts into an upward and then back to a downward. So we'll have to think how we're going to use the second derivative, if we can, to show that. How's the theory going to help us with that? So I want you to be thinking about these things. I don't want to just cast all of this upon you and say, oh, look, now that you can do this. Keep thinking about this, and when we get to it, we'll just fill in some of the details. So that means that we would look for a sign test of the derivative like we have here. This is set up for a simple sign test. We'll use this for increasing, decreasing. So the key with the derivative, as well as the second derivative, is to write it in a form that we have the one unit and the products and the quotients, so that we can analyze sign using boundary values. And then, of course, all of these zeros and actually the real numbers for which the derivative is undefined, they all exist to multiplicity 1. So it would be a crossing at every zero or every boundary value, which would make the analysis very, very simple. Okay, so that's kind of beating it to a pulp, but that's what we do with derivatives. Now, let's look at another one. Let's look at some trig. Now, what you're going to find with the chain rule is like the product rule, is that you just use it. You use it. You practice taking derivatives and cleaning them up, making them look nice. And then you can do exactly what I was saying. Perform the sign test and let that sign test give you even more information about the function. So that's the key. That's why we learn about theory of equations. We learn about factorization of polynomials. We learn all of that in college algebra and pre-cal. We work with trig functions. We work with conic sections. We work with sequences. All of these things are rudiments of the calculus. So we don't take calculus without any preparation. We clearly go through a series of mathematics to get us ready for this. So now let's look at the following function. We have f of x. Let me grab one more sheet of paper. That's a little bit easier to write. We have f of x equals 18 cosine x plus 9 sine 2x. And we're just going to look where x is like the unit circle, the basic traversal of the unit circle. So we're cutting down on the amount of analysis. So what the problem asks for here is, if I see this, compute, just like we did on the last one, even though I didn't take it to the very end, I was just doing the extra work to get you ready for this. And there's a lot of algebra when you're looking for horizontal tangents. So compute the horizontal tangent. So this is a problem where they say they exist. So look for it. Compute the horizontal tangents. And I'll just say, to be a little bit more clear, we'll say points of horizontal tangency. Notice before in the previous problem, I just noted the values of x where we had horizontal tangents. I did not compute the y value. And then we looked at points where we would have the vertical tangents, but those were on the axis, so that was simple. So if a problem may ask, and this is going to be a term we have later, the term will be critical points. And if we're simply looking for values of the independent variable where possibly the slope is zero, that is, we have a zero value of the derivative, or we have a value in the domain for which the derivative is undefined, just like we did in the last problem. So if you remember this, notice we had values in the domain for which the derivative was zero and also undefined. Later on, like I said, those will be called critical points. They are important, especially when it comes to sign values of the signs of the derivative and also optimal values. So if the problem is asking just for the critical numbers, we don't look for the actual y value, but it may be more specific and say points of horizontal tangency. So not only will you consider the zeros of the derivative, but you'll also compute the actual value of the function at that value of x. So we have an actual point on the curve, just like you did when you were working with your pre-calculus graphs, your trig graphs, things like that. That's all we do. So let's go ahead and do this. Notice here, now, many times you can factor the original function to make the differentiation process easier. That's going to be up to you. But notice here, the cosine x does not require the chain rule. But notice we have the sine of 2x. The inner function is 2x. So that requires the chain rule. So note here, this is not as complicated as the last problem algebraically, but it does involve trig functions, which will necessarily make the analysis probably a little bit harder, not necessarily a lot harder. But I'll just say here, we'll look at this and just remind ourselves that that will require the chain rule. And we don't want to overlook something like that. It's just not standing out at us. So now what I might do is just write f of x, because we're going to get a 2 out of that. So I'm going to go ahead and factor the 18. It's not required, but we look at this. It might help a little bit. Cosine x plus, and of course 9 over 18 is 1/2. And then sine 2x. So remember that the derivative operation is linear, so that we can factor constants and we just keep them to the side and differentiate everything else. So we factored this, and so now f prime of x, we just have the 18 and we just differentiate what's inside just using our knowledge of derivatives. The derivative of cosine is the negative sign. And then we can apply the linearity with the 1/2 here. Just put the 1/2 to the side. Multiply by the derivative of sine, which is cosine. So that's the outer derivative, cosine 2x. And then times the derivative of the inner function, which is 2. Okay? So again, this is the chain rule. The outer derivative times the inner derivative. Outer derivative, inner derivative. Always. It will take some practice to get used to it, but once you do, it'll be natural to do. Now notice, because I factored initially, the 1/2 and the 2 absorbed. And even if they didn't, it's not going to change the answer. You just have to do a little bit more arithmetic. Now, let's write what we have. So we have 18. And notice here, we've got cosine 2x minus sine x. And so we want to figure out if we have any horizontal tangents. So now we can just use the cosine of the double angle. Remember, one form of this is where we replace the cosine squared term with 1 minus sine squared. So we just get 1 minus 2 sine squared x. So this gives us a way to replace the cosine of the double angle with another sine function, which again will make this quadratic in sine. And of course, that'll be easier to analyze. So now we have 1 minus 2 sine squared x minus sine x. Now, if you like, we always like leading coefficients to be positive. And then, of course, this looks like this will factor. So I'll just leave the 2 where it is. So we have minus an 18. And we have 2 sine squared. And of course, we're factoring the negative. So this gives us plus a sine x. And then clearly minus a 1. But by AC, we see that the 2 times the negative 1, those 2 factors add to 1. So this does factor very cleanly. So negative 18, 2 sine x, and then of course a sine x. And we need the 1, so we're going to have plus 1, and then a minus 1. So now we see that we are set up for zero product, just like before. I mean, the key to the theory of equations is the zero product. Factorization allows us to employ the zero product, and that's how we solve most equations, and it's a very powerful result. So now we can set the derivative to 0 and use zero product. So if and only if sine x is transposed is 1/2, or sine x is -1. So when we look at that, we're like, okay, remember, we are interested in 0 to 2 pi. So this is just an upper arc calculation. We know we have 2 values. So we have x is the inverse sine of 1/2, which is pi over 6. Again, these are easy values. Otherwise, we just have to write them in terms of the symbols, but we know these are values on the unit circle. And then, of course, the other value in the upper arc is pi minus pi over 6. So we have 4x equals 5 pi over 6. That is in the upper arc. So this will give us the 2 values in this particular set. Otherwise, we just extend these by 2 pi n or 2 pi k. But we're only interested in this particular interval. Now, of course, here we know that sine x is -1 when we got what 4n plus 3 times pi over 2. That is congruent. What is it? The mod congruent to 3 mod 4 multiples of pi over 2. That was a lot. So, for instance, we know in general this would be x equals 4n plus 3 times pi over 2. And so we're just interested in the one that, that lives in here. So the n would be 0. So this would imply 3 pi over 2. So just remember, when sine is 1, we have 4n plus 1. So we've got multiples that are congruent. What is it? Integer multiples of pi over 2 that are congruent to 1 mod 4. And then we have integer multiples of 3 pi over 2, or just pi over 2, where we have the 4n plus 3. So again, just remember, 4n plus 1 times pi over 2 gives us the values when sine is 1. And then the 4n plus 3 times pi over 2 gives the values when sine is -1. So again, just as a review, we'll say, this is just an extra, just to have you review it. Here's an extra. We have sine x equal 1. So x is just 4n plus 1 times pi over 2. So that's the extra bit. So we have the congruent to 1 mod 4 multiple of pi over 2. So that, that gives you the 1, the 5, the 9, the 13, etc. Here, you've got the 3, the 7, the 11, the 15, 19, etc. And then, of course, you can go into the negative values. So that's just using the unit circle. And again, I'm not trying to give you overload here, but you may be in a class where you've got to generate more. And so this would be an easy way to do it. Just iterate the values of any. So now we've got the zeros here. And so we just want to evaluate them. So let's just put a box around each of them so we remember what they are. That'll be easy to evaluate 3 pi over 2. So f of pi over 6, go back to the original function up here, right there. So we have 18 times cosine of pi over 6 plus 9 sine. Of course, we have pi over 6 and the 2, so that'll give us a pi over 3. So, of course, we've got 18 times what? What does it give us? Root 3 over 2 cosine of pi over 6, again, unit circle, plus 9. And, of course, sine of pi over 3 is root 3 over 2. So we don't want to absorb anything, so that'll just give us 27 times root 3 over 2. Now, so again, a point of horizontal tangency would be pi over 6, comma, 27 root 3 over 2. Now let's do f of, okay, what? 5 pi over 6. Now you look at this function and see, if we replace, it's not an even function, nor is it odd, so we don't have the luxury of that. But the idea is that if you replace x with negative x, then that x absorbs, that negative absorbs, and then this one factors. So let me just write that down. So f of negative x, of course, that would absorb, so I'll just write it as it is, cosine of x, because cosine's even, and then we'd have minus 9 sine 2x, because sine is an odd function. So, of course, if you factor this, you just get negative, and then you have what? Negative 18 cosine x plus 9 sine 2x. So it doesn't have the nice properties, even though you're going to look at the answer we get and think it is. This is neither. It's not even, it's not odd, it's just nothing. So, and of course, we don't even have a symmetric interval here, but it still doesn't preclude us from at least trying to check that. But it's, so we'll just say in this case, neither even nor odd. Neither, if we were to extend it to symmetric, neither even nor odd. I mean, this is just a fabricated domain. These are clearly defined for all real numbers. So even if we wanted to extend it, we wouldn't get anything better there. So we have 18. So we have cosine of 5 pi over 6. That's a repetitious. And then we have, okay, now we've got the 2. So the 2 will absorb into the 6. So that's going to be plus 9 sine of 5 pi over 3. So just like we had before, we're in the second quadrant. Of course, the reference number is pi over 6. So this gives us what? 18 times a negative root 3 over 2. And then, of course, the sine of 5 pi over 3, the 5 pi over 3 is in the fourth quadrant. The reference number is pi over 3, so it's negative. So we get a negative root 3 over 2. So plus 9 times a negative root 3 over 2. So again, this will be a negative 27 root 3 over 2, just adding it up. So here's our first point of horizontal tangency. And so our second one will just look like this: 5 pi over 6, negative 27 root 3 over 2. Okay? Now the very last one, like I said before, is going to be kind of easy. We have 3 pi over 2 our friend, axial value. So we have 8 times cosine of 3 pi over 2 plus 9 sine. Of course, the 2 will absorb. We have 3 pi. Well, we love pi's for sine because that's 0. We love 3 pi over 2 for cosine, so that's 0. So that's just 0. So this gives us 3 pi over 2 comma 0. So we have 3 points of horizontal tangency for this function. Even though it's a simple function, we often find that the trigonometric analysis, even though it's all on the unit circle, it takes a little bit more time. And then, of course, it's nice to know how to do these. And when you study trigonometry, you sometimes forget that the mod 4 or the congruent to 1 mod 4, congruent to 3 mod 4. You know, it's just nice to know because those are quick answers that can help you when you eventually do PDEs and Fourier analysis. So again, we have 3 horizontal tangents, pi over 6, 27 times root 3 over 2 is the y coordinate. And then we have the other one. Let me go ahead and put a box around that. We have 5 pi over 6, and then negative 27 times root 3 over 2 is the y coordinate. And then we have 3 pi over 2, 0, where 0 is the y coordinate. Okay? So again, the power of the chain rule now allows us to do this problem, but then all the rest of the stuff is just old stuff. So calculus is just algebra, you know, what is it? Let's say fancy arithmetic, but we're doing a lot of arithmetic and trigonometric analysis from pre-calc. Okay, now what I wanted to do was talk about some in your homework, you have some absolute value calculations, and I thought this was kind of interesting. So you're given a formula. So for instance, if we can use the chain rule. If we wanted to take the derivative of the absolute value of u, so we're just going to take u to be a real expression, okay? And the problem gives you a formula for this. So let's derive it using the alternative square root of u squared and use the chain rule. So now we have, and let me use the 1/2 power. That way we have a little bit more, yeah, it's a little bit easier to see. So we have u squared to the 1/2. That's a positive or a non-negative quantity. And we can use this as a substitute for the absolute value of u, and it can be quite useful. So now we can apply the chain rule and the power rule. So the power rule with the chain rule, which is the generalized power rule. Long-winded, but you know, you never err in calculus where you at least solve what you're doing or speak it or think about it. There are lots of terms in calculus because you're dragging all the pre-calc, you're dragging all the college algebra to calculus. So there are lots of terms, and you have to think about them as you write them so that you use the correct mathematics. It's very easy to slip, but that's the nature of the beast, right? So now, by the generalized power rule, we have 1/2 u squared to the negative 1/2. And now times the derivative of the inner function, which is 2u, u prime. So this is like where we have an additional composition. We have the outer function, which is the square root function. Then we move into u squared, and then u. So u is an expression, real expression, it's squared, then it's square rooted. So we have 3 factors to consider. So the generalized power rule, the derivative of u squared, and then the derivative of u. So that's where we've got the three composition going on. So it's a little bit more complicated, but that's why we call it the chain rule. So now notice we have the 2 here that absorbs this 2. And of course, we can take this downstairs now. So we're left with u times u prime. divided by the square root of u squared. But of course, the square root of u squared is the absolute value of u. So in your problem, you're given u prime over the absolute value of u, which is fine. And that's a form that you want to use. And that's exactly what the problem gives you. So they don't ask you to derive it, but you can use this identity here and the chain rule to get that formula. So now the problem says h of x equals the absolute value of 6x times cosine of 8x. So this is great. So this means that we can use the product rule in conjunction with the what? Chain rule. Now, of course, this is not complicated. So, of course, the 6 we can factor 6, absolute value of x, cosine of 8x. So now, if we're just focusing on this, the absolute value of x, we're saying that the u is just x. So if we're thinking about this calculation, we'll just say that the u is x and u prime is just 1. Now, of course, you could think of that as another letter like a alpha or a v or something. Don't use the same letter, but this calculation is pointed at this particular function. So now we can use the product rule with the newfound results for the absolute value. So h prime, again, we can factor the 6. So now we'll just fill everything in. We'll have x times 1. So I'll just write it out. X times 1, just to be precise, divided by the absolute value of x, right there. Okay? So that's just using this formula, times cosine of 8x. Now we leave the absolute value alone, and we multiply by the derivative of the cosine 8x. So that'll be a negative sine 8x times the derivative of 8x, which is 8. And so we're done with that. So now if you want to multiply things out, this will be a 6x times cosine of 8x divided by the absolute value of x. Plus, just moving over here, well, of course, I won't do plus negative. I'll just go ahead and use the minus since we've got the minus there. So we've got minus 8 times the absolute value of sine, absolute value of x times sine of 8x. So now when you look at this, and of course, my bad, 6 times 8 would be 48. So I'll just add the 4 here. So don't forget 6 times 8. So now when you look at this, and this is in comparison to what you were asked to do in your homework, we see now that maybe this is a formula that's good to know. You don't necessarily want to have to do this, rederive it, unless it's just a very simple example. So if you keep this as a formula, then you can address it right away. That is, the derivative with respect to x of the absolute value of u is u times u prime divided by the absolute value of u, which again is convenient. And it was certainly very convenient here because we applied it directly. And we factored the 6. And so again, remember, like I say before, you factor numbers and you leave them to the left and then you forget about them. Please don't forget about it. So now here's one other example that uses this. And then I want to say a little bit about that power rule. So we'll cover that. This one was another example that I thought was interesting. And we'll use the newfound rules that we had before. So we've got, I'll use the 1/2 power here. We have x squared minus 12x plus 36 to the 1/2 power. And we're asked to compute g prime. So again, we're just looking at derivatives here as formulas. We're not necessarily evaluating them or looking for horizontal tangents. We're just getting some practice differentiating some interesting functions. But now what you can see is that this is just a perfect square. So this is what? X minus 6. This is what I teach my college algebra and pre-cal kids, and you know, indispensable because we carry all of this to calculus. And of course, this is just the absolute value of x minus 6 by definition. So now we can apply the result here. So if you will, it's just as simple as it was the last time. U is x minus 6, so u prime is 1. So let's apply it. So this implies g prime of x equals what? X minus 6, x minus 6. I'll just put the 1 there just to be complete, divided by the absolute value of x minus 6. So we just basically have this. That's it. So if you like, this is just x minus 6 divided by the absolute value of x minus 6. Now, of course, we can simplify this. This is just an identity because it's 1 where it's defined, or -1, right? So we can say we'll get x minus 6 divided by x minus 6, which equals 1. So we would just call it 1 when what x is bigger than 6, because we're just now evaluating the absolute value. And then, of course, when x is less than 6, we have the negative here for the absolute value. So we have x minus 6 divided by the additive inverse of x minus 6, which is now -1. So now the function could be defined as just 1. So I'll just kind of focus on this part. 1 when x is greater than 6, and -1 when x is less than 6, just by definition of absolute value. So that's an interesting problem, and very, very useful that we can apply this formula. So interesting things that you can get out of the chain rule. So you see, it's kind of like the necessity. We always say that necessity is the mother of invention. If we need to solve something, or if we need some tool to work on a problem, we've got to invent it or discover it or do something, put things together so we can figure things out. So I think this is a nice application of this, and a very elegant problem that now we can solve easily with the use of the chain rule. Now, so like I said before, the best way to do the product rule, quotient rule, chain rule is practice the algebra, clean up everything, apply good techniques to reduce, especially if you're looking for horizontal tangents, or as we were going to call them later, critical numbers. Keep the algebra clean and neat, and check yourself. Again, don't forget about constants. It's easy to forget them. You know, they're hanging out to the left and they just kind of fade away. And now, again, like I say, we have our derivative of the absolute value. I wanted to end by just going back a little to the power rule. We know the power rule is good for positive integers. You can use the definition directly. Now, let's consider a situation where we would have an integer that's less than 0. That is -1, -2, -3, things like that. So for instance, consider n an integer. So z is our integer, the German Zahlen, that means the integer, where n is less than 0. So we're thinking -1, -5, things like that. Then we could say that x to the n can now be written a little bit differently. That is, we can write this as 1 over x to the negative n, okay? I know that's kind of cheap, but now note, and let me just say, observe that negative n is now positive, and negative n is an integer. The additive inverse of n is a positive integer, and we have that rule. That is, we proved that using the definition, and you can see that in the lecture notes. So with that result, we can now move into negative integers where it didn't work, because now minus n is a positive integer, and we can apply the rule that we proved previously, or that we found in the notes as being true. So now this implies that x to the n prime will now just be this. Now I'm doing we can do this two ways. I mean, you're thinking that this is just the generalized power rule, and I agree with it, but I wanted to go back to the quotient rule because that's when I should have done it. So now when you look at this, we can just apply the quotient rule. So we have 1 prime, well, that'd just be 0, times x to the minus n, minus 1 times, and that will apply the power rule. This will be negative n times x to the negative n minus 1, just applying the power rule, which we know to be true for positive integers. And then we square this, so this is x to the minus 2n. So I'm not using the result from the chain rule because I'm using the previous result. And I should have said something before this, but now, of course, like I said before, you're just thinking this is just the generalized power rule. But in order to do that, we really needed to have said something about this with the quotient rule. So now that's just a 0. So we have 0 times that. So that's a 0. And then minus minus. So we have plus n x to the minus n minus 1 divided by x to the negative 2n. So now we have n. And now we can subtract the powers. So we have x to the minus n minus 1 minus the negative 2n, which is just the laws of exponents. So that gives us nx. So we have a minus n plus a 2n. Well, let me just write it out. Minus n minus 1 plus 2n. Using the negative of the negative, the additive inverse of the additive inverse. So this is nx n minus 1, which is what we wanted to show. So when we got the quotient rule, we actually had a method to show the power rule is valid for negative integers. So we had the positive integers initially, now we have the negative integers. So that's good, that's good. Now, what's left? So let me just write here, we'll just say power rule valid for z. And so, of course, when we use the chain rule, we just use it and we say it's valid for z and rational numbers. So to get to the rational numbers, like I said before, we're going to need a new operation called implicit differentiation. And that will allow us to basically look at transforming derivatives from the explicit realm to the implicit realm, which is basically the implicit function theorem. I mean, when we do the inverse function theorem, we think about finding derivatives of inverse functions without having to know the formula. Okay, so that's a grand result. And then when we look at the implicit function theorem, again, we're taking derivatives implicitly. We don't even have the explicit formulation of the derivative. And so we are able to compute values of a function for which the possibility of writing down an explicit version is impossible. So we're at least good that we have the power rule for this. We will get the power rule for rational numbers, ratios of integers, which will at least make us feel better, because right now we were just kind of walking on thin ice, keeping our fingers crossed that the power rule worked. It does. We now, of course, have the really, really nifty result of the generalized power rule. But we really, in order to use that, we need to know that this actually does work when we just have plain old x to the -3. Now we know that's going to be what? That's going to be -3x to the -4. Bring the -3 down, subtract 1. So we can do that with confidence. So I wanted to add this because I did not do it before, but the proof is simple, just a simple application of the quotient rule. So let me just write here, quotient rule. So as we learn new theorems, we can apply them. And of course, lots of times in calculus, we'll make assumptions, and then as we gain more clarity and more maturity, we can go back and fill in some details. Okay? Well, I hope you've enjoyed the excursion into the chain rule. It's certainly a huge result, a very important result, and we will have plenty of opportunities to use it. So practice, like I said before, practice the computation, product rule, quotient rule, chain rule. Many rewards with doing that. As you develop a good sense of the algebra and how it combines with the calculus and the arithmetic, you will definitely be rewarded by that. And as we move into the end of this chapter and then go on into more theory of the derivative, we will definitely benefit from that. Okay? Well, I hope, like I say again, keep busy, and I'll see you soon.